For this next section, we're going to continue to talk about the Pythagorean theorem, but we're going to get into the proof behind the Pythagorean theorem, and then we'll also talk about something called the Pythagorean theorem converse, and we'll see when we would need to use that and why we would maybe need to use that. The first thing that we're going to start out with, though, is the proof behind Pythagorean theorem. Okay, Pythagorean theorem is like this really big deal in math. You know, we use it a lot, especially when we talk about right triangles. We saw it show up in quadrilaterals last semester. You've seen it kind of pop up sporadically so far this semester. So we're going to continue to talk about it today. But before we get into the converse, I want to go over why does Pythagorean theorem work? What is the proof? What is the stuff that was done years and years and years ago by Pythagoras and like the, all the people that were involved in that? How did they come to this conclusion that a squared plus b squared equals c squared? Like, where does that come from? So we're going to use what we've been talking about the last couple of days with similar triangles. We're going to be talking about setting up proportions still with like our geometric mean, those kind of things, okay? So remember from what we talked about the other day, we had a picture similar to this when we were talking about geometric mean, and we broke it into the three triangles, okay? The small one, the medium one, and the large one. What I'm going to do first is just kind of take all the information that I can from each of those triangles and label them down here. We've done this before, so think back to when we did that with the geometric mean problems. We just took what we could from the pictures and we put them on here. So for the small triangle, we're going to call this side the A, across from that 90 degrees. We know that the smaller piece is D at the bottom. And then we have this angle. Other than the 90 degrees, we have this angle, this little like star. So I'm just going to put that down there. Okay, then if I look at my middle triangle, now think about two. This one's kind of on its side, so be careful when you're labeling your sides here. The right angle would be here. And so it looks like the side across from this right angle is where that B is at. So that's going to go on that hypotenuse side. We have the longer of the two legs is E. And then that space up in between those is an open circle by that angle. Okay? Now the big triangle, your right angle would be here. What could you label the hypotenuse with? C. And what can we label the shorter leg? A. And then the taller leg is B. Good. And then we still have these angles. We have a little star down in this corner between A and C, and we have an open circle in that corner between C and B. Okay? All right, now we've used this before for geometric mean. Today I'm going to kind of walk you through, still kind of thinking back to that, but how does this apply to our Pythagorean theorem proof? So they're providing us with this given information that says a right triangle that has this altitude drawn from the right angle to the hypotenuse, okay? All I'm going to write down here, and we're only going to put statements. We're not going to necessarily be putting reasons for this, is we're going to I'm just going to kind of draw an arrow for my given here, and I'm just going to write for step number 1 that the triangles are similar. Okay, all three of those triangles are similar. And that's kind of what they're saying in the given, is that you had this right triangle. It's got this altitude drawn in it that's creating these two smaller right triangles. All three of them should be similar to each other. Okay, now let's think back to like our geometric mean idea, because I want to set up some proportions. Because eventually I want to be able to show that the a squared plus b squared equals c squared is going to pop up, but I have to be able to do that somehow. So think back to when we were setting up geometric mean, we were always looking for a quantity that was shared. In this case, if I look at my three triangles and specifically look at my sides, my A is shared on the little triangle and the very big one, and B is on the middle triangle and on the big one. So those are like shared sides that we can maybe try to put together. So I'm going to write out a couple of proportions here with my A and with my B kind of in mind. So for my A's, from the little triangle, I have to use the A and the D because those are the only two sides that I have. So I'm going to put D over A. And then what would that match from the big triangle? How would I set up the second half of this proportion? Yeah, it would be C over A, right? Or I'm sorry, A over C. I said that wrong. Okay. So those pieces are going to kind of go together from our two triangles here. Then let's do the same thing, but now let's try to use our b twice, because I'm going to kind of just even give you a little heads up here. We're going to eventually, on the next step, we're going to be talking about cross multiplication, and then a squared is going to appear. Okay, I need a b squared to show up too, because I know that that's part of Pythagorean's theorem. So how could I set up a proportion with my b's? Good, you could do E and B from the middle triangle, and then that would go with B and C from the big triangle. Okay, and again, the next step is we're going to cross multiply, and I want us to write out what it looks like now. So now that we have those like terms together, if I cross multiply, I'm going to get an A squared equals CD, and I'm going to get a B squared equals CE. Okay, now this next step is we have to, eventually get to this. This is our end goal, a squared plus b squared equals c squared. So I want to kind of rearrange this. And because I know that these are similar triangles, that's what allows me to do this. Like I can start to kind of manipulate what these two things say and be able to kind of start putting things together. So what I mean is if I have just the a squared and just the b squared and I'm trying to add them together, we know because of our sentences that we wrote in statement number 3 that since a squared equals cd and b squared equals ce, that if I add those together, that should equal the same amount as whatever a squared plus b squared is. So I'm taking these pieces from my cross multiplication here, and I'm just trying to kind of lump them together in a way that's going to work for me. But I'm not saying anything that isn't true here. Because a squared was equal to cd, well, I have a squared on one side and I have cd on the other side of the equal sign. And I'm saying that b squared was also equal to ce. Again, those are on opposite sides of the equal sign. If I'm adding those quantities together, I'm just making a longer statement, but it says the same thing as what I said in number 3. Now, the reason why I want to do this is because I want you to look at this second half of what I wrote. Do you guys see anything that's shared in that statement on the part that I underlined? We have something in math called factoring. And some of you may know how to factor. You've maybe had to do some factoring like when you were in algebra, okay? So factoring is when we look at terms or a bunch of numbers or even letters, and we try to see, is there anything that they all have in common that we can take out? So in this case, I see that there's a C in both here. So I'm going to factor the C out. So if I take a C out, then I have to write what's left over, which would be a D plus an E. Okay? And then I'm going to go ahead and bring everything else down. A squared plus B squared is now equal to this C that I factored out, now times D plus E. All right, now you might be thinking like, well, why are we doing that? What's the point here? I need to get to a c squared, right? Because I already have my a squared plus b squared. If you look at what we just wrote in our parentheses, d plus e, and you look at what those are up here, are they the same thing as c? If I put d and e together, isn't that the same length as whatever c is? You guys seeing what I'm saying there? If you knew that c was 10, and you know that D is 3 and E is 7, don't 3 and 7 also make 10? So I should be able to now say that this is really a squared plus b squared equals c times c. I can use substitution to replace that fact that d plus e together is going to also equal c. Now, if you look at this, what would be c times c? C squared, right? So then we end it with a squared plus b squared equals c squared. All right, now when we get into what we're going to do next, we're not writing proofs, okay? But it's really important that we understand Pythagorean's theorem proof. Just like in the past we had to prove like why vertical angles worked, why corresponding angles were always going to be equal on parallel lines. Like we had to prove those things in order to use them in like the coming things. Like we've already now done, even in this semester alone, when you had to write proofs with similar triangles, you were still using vertical angles, alternate interior, corresponding, right? We've already done all the hard work in proving those things. So we needed to be able to understand, where does Pythagorean's theorem come from? It's not just this idea that somebody decided to come up with in math one day and be like, yeah, this works. There was a lot of like time and effort put into how Pythagorean's theorem works and why is it this way. So we needed to go over that proof so that you guys can really understand the background knowledge. So when you're using it later, or if you're using it to justify why you know something, we don't have to go back through and do that whole proof again. Okay. Now I will just kind of give you a heads up. You're going to want to memorize this proof because it's going to show up on your test. We've had proofs like this before where I've told you in class, make sure you're memorizing this proof because it's going to show up in your test. Okay. It's no different than that. Yes, it's maybe 7 steps, but you guys should be able to kind of work your way through this by setting up proportions, cross multiplying. None of the stuff that we put in here is super difficult math. Okay, we're just setting up things with our geometric mean idea, cross multiplying, and so on. So make sure you're spending some time reviewing over that. You've got plenty of time before that test is coming. So I would just even start later today. Take out your notes, look over those 7 steps. Can you write out any of them? Start with whatever you know, and then go back in, memorize the other stuff, look over again, what did you miss, and then start filling that in, and try to do that daily. It'll help you kind of have that more solidified before you take your test, okay? All right, so we're going to kind of move away now from the proof, and we're going to come down here to these last couple of examples. And what they're asking us to do down here is to use this thing called the Pythagorean theorem converse. Converse is a way in math, when we're talking about proofs, that it's like you take the original idea that you had and you reverse it, okay? So, for example, I would say, if you have a right triangle, then that means you can use a squared plus b squared equals c squared, okay? If you have a right triangle, you can use Pythagorean's theorem. What the converse says is, if you can use Pythagorean's theorem, then you must be working with a right triangle. So it's the same kind of rule, but it's flip-flopped. It's backwards now on us, okay? So what we're going to do is we're going to test and see, are these 3 triangles down here right triangles, or are they actually an acute triangle or an obtuse triangle? Now let's talk about how you tell the difference. So if a triangle is right, then, that statement a squared plus b squared equals c squared is true, okay? I'm going to write this down here at the bottom where I've got maybe a little bit more space to do this. So if I know that a squared plus b squared equals c squared, that means I'm dealing with a right triangle. Okay, if it's true, I plug in my a, b, and c, it equals itself on both sides, it's a done deal, Pythagorean theorem works, it's going to be a right triangle. Okay, if a squared plus b squared is greater than c squared, so when you plug in your sides, you get a bigger number on the left side than you do on the right side of the equal sign. This means that you're dealing with an acute triangle. So then what do you think it means if a squared plus b squared is less than c squared? Yeah, it would be obtuse. Okay? So if you think about it, if it's a right angle, then it's going to work in a squared plus b squared equals c squared. It's going to guarantee that that corner is square. Okay? It's going to make sure that there's 90 degrees. If the 2 legs are bigger than the hypotenuse, that means that that hypotenuse is going to be smaller, so those 2 legs are going to be forced to come towards each other, which is going to make that an acute angle in between them. Now, if the hypotenuse is bigger, and so your a squared plus b squared doesn't get bigger than your c squared, that means they have to stretch out farther to touch the ends of that c side, and so that's going to cause an obtuse angle to show up. That's why this works the way it does. So when you look at these 3 pictures down here, you don't know for sure if they're right triangles. That's what they're asking you to figure out. You're going to have to make some assumptions, though, on if it was a right triangle, where do you think the right angle would be? Okay? So on the first one, letter A, where do you think the right angle might be? Okay, I agree. I think it would probably be about here. All right, now I don't know that for sure. So what I need to do is set up my a squared plus b squared equals c squared and see if it checks out, see if the math matches. So what would be your A and your B? Good, the 4 and the 12, which means 13 has to be your C. Okay, so now let's do the math. What's 4 squared and what's 12 squared? Okay, 13 squared. Good, okay. If we add 16 plus 144, what do we get? We get 160. That's not equal to 169. It's actually less than 169, right? So the a squared plus b squared is smaller than the c squared. What kind of triangle are we working with then? Good, obtuse. So I'm going to say no because it's not right, and I'm going to say this one is obtuse. Okay, let's go on to letter B. Where do you think the right angle would be? Okay, up in this corner here. So what are your A and your B? They're those square roots, right? Because the 4 would maybe be in the C spot. So if I was going to write this out, I'm going to put the square root of 10 in parentheses because I'm going to be squaring that because that's my A maybe. And then the B is going to be that square root of 6, and I'm going to square that too. I'm putting parentheses around it just to make sure that you see all the symbols there. And then that equals 4 squared. Now, do you remember from past conversations, what happens when you square a square root? What was that shortcut we talked about? The number just pops out, right? So 10 comes out, no more square root, and 6 comes out. Okay, what's 4 squared though? Good, 16. So 10 plus 6 is 16. So this time they equal. So what kind of triangle do we have here? That's right, we have a right triangle. Okay, why don't you guys try to do letter C? Okay, so you think your right angle would be about here. So then if we set this up, we would have the square root of 14 squared plus the square root of 5 squared equals 4 squared, maybe, potentially, right? What happened here? Good, the 14 and the 5 come out. What's 4 squared? 16. What'd you get? 19 is greater than 16. So is this a right triangle? No. What kind is it? Good, this one's acute. All right, do we have any questions on that?